Hello and welcome, Mr. Johnson here, and in this video we're going to be talking about intermolecular forces or IMFs. So let's go on and get to it. So when we're dealing with intermolecular forces, again, as always, the first thing that we need to do is define exactly what it is that we're dealing with. So when we look at the definition of an intermolecular force, or again, what's also referred to as IMFs, these are forces or attractions between molecules, typically of solids or liquids, even though we can also talk about IMFs for gases. Just we typically don't, because gas particles are so far spread apart that there's really no attractive forces to them. Okay? So primarily IMFs is when we're dealing with solids and with liquids in the interactions or the attractive forces between one molecule and a neighboring molecule. That is an intermolecular. Please don't get this confused for something called an intramolecular force. An intramolecular force is actually, in essence, a chemical bond, okay, ionic or covalent, which if you're not sure about what an ionic or covalent bond is, take a look at my previous video that I did on bonding, and that should answer any questions you have regarding covalent or ionic bonding, as well as metallic bonding. Okay, but those type of things, bonding, those are intramolecular. What this video is dealing with is inter, so between molecules. Okay, and when we're going to be looking at these, the important thing to understand again is that difference. So look at this particular image that I've got on the screen for you. When we look at this molecule of HCl or hydrochloric acid, okay, the bond between the hydrogen and the chlorine, that is a covalent bond. That is also what we'd refer to as an intramolecular, okay, intramolecular force. The other thing with this, if you look at the electronegativities between hydrogen and chlorine, you would find that hydrogen and chlorine have a significant electronegativity difference. That makes this a polar covalent molecule. So I've got a region of positive charge and a region of negative charge. And the same is going to be true on both of these molecules neighboring. So what we end up getting is an attractive force between the negative pole of one molecule and the positive pole of the other molecule. That is my intermolecular force, or my IMF, that force of attraction between one molecule and the next. When it comes to IMFs, please understand that these vary in strength, but they're generally weaker than an actual chemical bond. Again, weaker than your ionic, your covalent, and your metallic, because when we're dealing with IMFs, there's no actual physical interaction between the molecules. It's just an attractive force. Okay? So that's why we refer to these as IMS, intermolecular forces, rather than as a type of bonding. Bonding is within a molecule. A force is between molecules. So please make sure that you're clear on that distinction between bonds and forces. Okay? So when we're looking at IMS, there are four basic types of IMFs, and we're going to look at them going from strongest to weakest. Okay, some places you'll see that they say that there's 5 basic forces, but I'll explain why I'm just going with 4 here in just a moment. Okay, but the first of these is what is referred to as a network solid, or it used to be referred to as a network covalent solid. Okay, and this is a solid molecule that is a 3-dimensional network of covalently bonded atoms. Okay? So a couple of examples. First off, diamond, graphite, sand, or silicon. These are all network covalent solids. Okay? So take a look. This is a model of a diamond. Okay? So it's a 3-dimensional repeating structure. And if I remove kind of one segment of this, it doesn't diminish the rest of that molecule. It doesn't diminish that network. So this is a network solid. Okay? Same thing when I take a look at graphite. This is the molecular structure of graphite. And again, if I take a look at this, if I remove one of these, it doesn't diminish the rest of the network. So this also is a network covalent solid or a network solid. Okay? By the way, graphite, that's your pencil lead. When you scrape it across your paper, the frictional force between the pencil lead and your paper is enough to break these intermolecular forces and just leave this molecule after molecule actually all across your paper. Okay, so that's your pencil lead. So network covalent solid, that's your first type of IMF, and it is your strongest. Okay, so because it is a network, we've got a lot of intermolecular forces going on within that structure. And as a result, we typically find that network solids are going to have extremely high melting points. They're going to have extremely high boiling points. Okay? So if you go on to take an advanced science, advanced chemistry, or college chemistry, one of the things they'll have you do is identify an unknown based on melting points. So the higher that melting point, it's a good indication that you've got a network solid, or at least very strong intermolecular forces within that particular molecule or between those molecules. Okay, so that's the first type. The second type of IMF is what's called a dipole-dipole force, and these occur between two oppositely charged parts of different molecules. So in other words, I've got two polar molecules, and they come into proximity with each other, and the positive pole of one orients to the negative pole of the other. Okay? As far as why we call them dipole, it literally means two poles. If I've got a single molecule that is a polar molecule, it's going to have a positive pole and a negative pole. And again, this part isn't making sense. Go back and watch my previous video on covalent and ionic bonding. When I talk about covalent bonding, I also talk about polar molecules and how you get a polar molecule. Okay? But in a polar molecule, you've got a region of positive charge, a region of negative charge. So dipole, two poles. And when we look at these poles, okay, we represent them with a hashed or a crossed arrow, where the cross part of it represents the positive part of the first molecule. The actual head of the arrow represents the negative part of the second molecule. Okay, so let's take a look at a couple of examples of this and outline how this all works. Okay, so in this upper right hand depiction on your screen, what it's showing is really three different things. One, where you don't really have any type of polarity. There's no pull of the electrons within a particular atom or molecule or between molecules. So as a result, this is nonpolar, and you wouldn't have a dipole-dipole. But then what they go on and show is that if you look at a molecule, I'm outlining in black, those electrons get pulled to one side, and as a result, I get a region of negative charge and a region of positive charge. In my second molecule, the same type of thing. The electrons gather to one side or clump, and again, I get a negative region and a positive region. So what I've got is this pull, okay, between those two molecules. And depending on the polarity of the molecules, you can either get a very weak dipole-dipole interaction or dipole-dipole force, or you can get a large dipole-dipole force. Okay? The other thing in the upper left-hand one, it's showing orientations. I can either orient the two molecules where one is in essence sitting on top of the other. And again, I'm going to have that negative attracted to the positive attracted to the negative. So if we were to draw these arrows, as talked about, on one side we'd have this arrow, on the other side we'd have the other arrow. You can also get this, as I was showing in that earlier depiction, this type of thing where it's referred to as linear. And that's what, when I just put a star by, is also showing a linear dipole-dipole interaction when we're looking at iodine monochloride, okay, and the way that pulls. The last one, the bottom right-hand corner, this is showing an ionic compound, a sodium chloride. And when you have an ionic compound, this still has dipole-dipole, but we actually refer to it as a lattice, Lattice, lattice dipole. Okay? And the idea is that this sodium that I just circled belongs not only to this chlorine, but also this chlorine. Okay? So as a result, what we find is that lattice dipole-dipole, their strength is pretty much right up there with a network covalent solid. Okay? And in fact, sometimes a lattice dipole for an ionic compound, it's an even stronger intermolecular force than what you get with a network solid. Okay? So that's just some examples of dipole-dipole, and the second type. Now, the reason why some places are going to tell you that there's 5 types of IMFs is they count hydrogen bonding as its own unique type of intermolecular force. But in reality, dipole-dipole is just a special type. Hydrogen bonding is just a special type of dipole-dipole. Okay? And when you have hydrogen bonding, this is a force of attraction that is going to be associated with a polar molecule that contains a positively charged hydrogen. In other words, electrons have been pulled away from that hydrogen, like in water, water being a polar molecule. As the electrons are pulled away from the hydrogen, that hydrogen becomes positively charged. It's actually just a region of positive due to, again, polarity. But you've got that one molecule with that positively charged hydrogen, and it's in proximity to a second polar molecule that is negatively charged. And in that second molecule, you have to have oxygen, fluorine, or nitrogen. In fact, you'll see a lot of places that do this thing phone to phone. Phone is F-O-N, fluorine, oxygen, nitrogen. And when you do phone to phone, pretty much what it means is you've got a fluorine, an oxygen, or a nitrogen bonded to a hydrogen. Those electronegativities are such that it creates a region of positive charge around that hydrogen, and then that hydrogen is in proximity to a second molecule that has hydrogen also bonded to a fluorine, oxygen, or a nitrogen. So they call it a phone to phone, F-O-N. Okay? But when we're looking at hydrogen bond, as I said, this is a special type of dipole-dipole. And it's actually stronger than your just regular old typical dipole-dipole. So really it's network covalent solid at the top of the scale, hydrogen bonding, and then your typical dipole-dipole. Okay, so some places talk about those as being your top 3. I go on to talk about it as network covalent solids, dipole-dipole, and I break dipole-dipole into 2 categories, your typical and your hydrogen bonding being the stronger of the 2 types of dipole-dipole. Okay, so hopefully that makes sense. But even still, hydrogen bonding, it's relatively weak attractive force in comparison to network covalent solids. Again, I think about that scale, network covalent solids are way up here, hydrogen bonding is down here, and then dipole-dipole below it. Okay, and when we denote hydrogen bonding, we use these little dots. Okay, so you can see in this one, as I go to full screen again, what I've got is a molecule of water where, again, I'm going to have a positively charged hydrogen due to it being a polar molecule, and that's in proximity to another molecule that contains that negatively charged oxygen. So my hydrogen bond really is between the positive polarity of a hydrogen on one water molecule and the negative polarity on the oxygen of a second molecule. Okay? I could just as easily throw say, hydrogen fluoride in here. Okay, hydrogen fluoride, that fluoride, the electronegativity difference would give it a negative. And even on this, what I would see is a hydrogen bond between the hydrogen of one of those water molecules and the fluorine of that hydrofluoric acid. Okay? Because I've got a phone to phone. I've got the oxygen for on one molecule, my fluorine on the second molecule. I've got that positively charged hydrogen on molecule 1 and that negative region on my second molecule. Conversely, if I throw something into this like hydrochloric acid, okay, this will not produce a hydrogen bond because, again, that second molecule, if I count the water as my first molecule, this second molecule has to have oxygen, fluorine, or nitrogen, and HCl doesn't have it. So therefore, no hydrogen bonding takes place. Okay, so that's the key thing with hydrogen bonding. Okay, so that is, again, second type, dipole-dipole, but a special type of dipole-dipole. The third type, oh, and I forgot to mention, hydrogen bonds, again, because they're fairly weak attractions, these are easily affected by changes in temperature. If I heat this up, those molecules are going to speed up. There's a phrase that we use in chemistry, heat them up, speed them up, or heat them up, speed them up. And the idea is I've got these attractive forces. This is a water molecule, another water molecule, the way that they orient. As I heat those up and they start vibrating more and more, I'm going to spread those molecules apart, and therefore that attractive force is going to decrease. Okay? You can also change them with changes in pH or changes in ionic solutions. If I add, say, salt to this, it can disrupt that hydrogen bonding. Okay, so first type, again, network solids, dipole-dipole, of which hydrogen bonding is a type. Third type, this is what's called an induced dipole moment. Okay, and this is where you take a non-polar molecule and you get it to behave as though it is a polar molecule, but only temporarily. So induced dipole moment, sometimes you'll just hear referred to as a dipole moment. They won't call it an induced, but so that we cover everything, I'm going to go on and call it an induced dipole moment. Okay, but if you hear just dipole moment, same thing. Okay, so this is the way I think about induced dipole. If you think about a cafeteria, all the students sitting, everything's nice and calm. The students are your electrons, milling about, minding their own business. And then a fight breaks out. Well, that fight is like a positive ion. And all the students as electrons are going to rush over to see what's going on, whether they should or not. But as soon as they get over and they see that the fight's already ended, they spread right back out. That's an induced dipole moment. And there's actually two types of induced dipole. You can get an ion-induced dipole or a dipole-induced dipole. Okay? So this is the way it works if we take a look at this particular diagram or this image. So my red sphere, that is my neutral atom. And then in B, part B of the figure, I introduce a cation, a positive ion. And all the electrons within that neutral atom sense that positive charge, and they rush over to see what's going on. And in that moment that all those electrons crowd over to one side, what that does is it produces a region of polarity, that induced dipole moment. The other way I can do this is to introduce, like they show in figure C, a dipole. They show a positive side of the dipole coming in, and again, all those electrons are going to crowd around because they sense that positive charge, and again, it's going to induce a polarity. And once I induce it in one molecule, it can then induce this in a second molecule, which induces into a third, induces into a fourth. So this ends up becoming almost kind of a ripple or a domino effect, that all you got to do is introduce a cation or a dipole, induce a dipole in a molecule, and it passes that polarity on. Because again, if I had a third molecule sitting out here, as soon as it senses that region of positive charge, all of its electrons are going to rush over to see what's going on. and now I've induced another dipole. Okay, so that is your induced dipole moment. So we've got 3 under our belt now. Network covalent solids, those are your strongest. Dipole-dipole, which hydrogen bonding is part of, and hydrogen bonding, again, is stronger than your typical, just regular old dipole-dipole. Then we've got our induced dipole. That's our third. So our fourth type, this is what's called London dispersion forces, or LDFs. And this goes for nonpolar molecules. And these are extremely temporary. They last for a fraction of 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 a second. Okay? But the reason why they exist is because as those electrons within a molecule are moving around, free to move, just by happenstance, at some point, all the electrons kind of crowd to one side. And it produces, again, a temporary clumping or dispersion of electrons. I get that negative polarity on one side of the molecule, positive polarity on the other, and that induces the next molecule over to do the same thing, just like an induced dipole. Difference is London dispersion forces are very, very short-lived, and they're very, very weak attractive forces. Okay? So when we look at this, again, it's a temporary clumping due to all the electrons in motion within a molecule suddenly ending up on one side just through random chance. And as they end up on that one side, I get a positive, a region of negative charge, leaves me a region of positive charge, and that can then induce polarity in those other molecules. Other thing, London dispersion forces are also referred to as van der Waals forces or van der Waals interactions. So if you take biochemistry and you study enzymes, you'll talk about London dispersion forces or van der Waals interactions. Okay. Other key thing, any atom or molecule can have these type of forces because every single atom or molecule has moving electrons. Okay. This is the only type of IMF that noble gases can have. This is what keeps molecules of hydrogen together, of helium together, not hydrogen, sorry, helium together, neon, argon, are these London dispersion forces. I also want to mention this real quick, and I forgot to put it into the slide, but molecules can have more than one type of IMF. Okay? If I look back at water, it's got moving electrons, so it has London dispersion forces automatically. But then it also has polarity, which means it has dipole-dipole, but then also, because it's got hydrogen, it also has hydrogen bonding. So for water, I've got multiple types of IMF. So please don't think that just because you've got one IMF, that's the only type that you can have. You can have multiple, okay? So this is the way that London dispersion forces work, like I was talking about. You get this clumping of electrons within an atom. That leaves you a region of negative charge, region of positive charge, and that induces in a second molecule or a second atom, and therefore you get this electrostatic attraction. Okay. Here's a helium nucleus, a helium atom, and again, if those electrons clump to one side, it's what we refer to as an instantaneous dipole. I get a region of negative charge, a region of positive charge, and then it induces a dipole in a neighboring helium atom. Okay. So last little part of this, factors that affect IMFs. Okay. There's a couple of different ways that we can affect IMFs. The first of those is temperature. Just like I talked about with the water molecules, if I heat them up, I speed them up. And when you speed them up and they start moving further apart, you're going to weaken those attractive forces. Conversely, if I cool them down and I force those molecules closer together, I can increase those IMFs. pH also changes it, especially when you're dealing acid-base chemistry. IMFs play a large role in whether or not something is a strong acid or a weak acid. Magnitude of polarity. The more polar a molecule is, the stronger the dipole-dipole interaction can be, or the stronger the induced dipole that it can end up causing with another molecule. Okay? And then lastly, the complexity of the molecule. What we have found is that the larger the molecule, the stronger the LDF, the London dispersion force. Because the larger the molecule, the more complex it is, the more electrons you have. And the more electrons you have moving around, then when they all do clump, you've got a larger clump of electrons and therefore a larger LDF. Okay, so the complexity of the molecule, and that complexity, what we talk about is something called polarizability. So another term for you, the last term, polarizability is simply the distortions of the electrical cloud because of the electrical charge associated with that clumping. Again, if you look at these diagrams, if I clump just a small amount, I get a small polarizability. Okay. Again, equal clumping, this would be like a non-polar, other than towards the ends, you can see the red, I get a much higher polarity than I do in the center. And then this here, again, a large electronegativity difference or a large complex molecule, larger polarizability. Okay, so hopefully all this made sense, but if you've got questions or you've got ideas for future videos, please leave them in the comments for me. I would love to hear from you. Love to have ideas for videos that you will find helpful. Again, hopefully you found this one helpful. So thanks for tuning in. Take care.